All right, so we have been looking at the relationship between the mean of a population and values of a random variable. So we've been looking at mu and our population standard deviation and changing our x values or our data entries into z-scores. So now we're going to start looking at the relationship between the population mean and the means of samples taken from that population. So remember, a sample of a population is just a subset. So if we're looking at students at Basehor Linwood High School as our population, then a subset or a sample would be at the senior class. Female students, students in the top 10% of their class. Okay, so each of those are different samples. And what we're going to look at now is if we take each of those samples, some of them may overlap, but if we find the mean of each of those, we're going to look at what's the relationship between that and the actual population. So a sampling distribution is the probability distribution of a sample statistic that is formed when the samples of size n are repeatedly taken from a population. If the sample statistic is the sample mean, then the distribution is the sampling distribution of sample means. Okay, so every sample statistic has some sort of sampling. All right, so we can note that sample means can vary from one another and can also vary from the population mean. This type of variation is to be expected, and it is called the sampling error. Oops. Okay. So this is kind of a diagram kind of showing you that you have your population and then each of your samples within it. Notice the X bar with the subscript representing our sample mean for each of those little subsets. So we have two properties of sampling distributions of sample means. The first one says that the mean of the sample means and we denote that as mu of X bar is equal to the population mean. Which is our mu. Okay, so we know that the mean of the sample means mu of X bar equals the population mean. Okay, so what that means is if we were to take each of these means and find the mean of them. So here that mu of X bar would equal X bar subscript 1 plus 2 plus 3 plus 4 plus X bar 5 divided by 5. Okay, so the mean of the means. All right, so then we can look at our standard deviation. So the standard deviation of the sample means which we denote with sigma of X bar is equal to the population standard deviation sigma divided by the square root of the sample size. Which remember we use n to denote sample size. So, oops, sorry about that. So our standard deviation of X bar equals the standard deviation divided by the square root of n. So the standard deviation of the sampling distribution of the sample mean is called the standard error of the mean. So that's another word or phrase that you'll see in your homework. Okay, so a lot of times instead of seeing find the standard deviation of the sampling distribution, you'll see find the standard error of the mean. Okay. All right, so then we have this example, kind of breaking it down and showing you how and why we can skip doing the actual calculations for the mean of the sample means and the standard deviation of the sample means, and instead show how these formulas work. For time's sake, I'm going to just refer you to look at page 262 in your textbook. Okay. So this is all on page 262, and it breaks it down step by step. All right. So now that we've looked at that, we can then look at the central limit theorem. The central limit forms the foundation for inferential branch of statistics. This theorem describes the relationship between sampling distribution of sampling means and the population that those samples are taken from. The central limit theorem is an important tool that provides the information you'll need to use sample statistics to make an inference about a population. So we have two statements in this theorem. The first one says if random sample of size n, where n is greater than or equal to 30, are drawn from the population, with a mean of mu and standard deviation sigma, then the sampling distribution of sample means approximates a normal distribution. Okay, the greater the sample size, the better the approximation. Okay. And we're going to look at a chart below here in a bit, kind of describing that. But basically what that's saying is that if you have a sample where n is greater than or equal to 30, and that's drawn from the population, and you know your mean and your standard deviation, then we can assume that that sample is normal distribution, despite whether it is or not. Okay. And the second part of this theorem says that if random samples of the size n are drawn from a population that is normally distributed, then the sampling distribution of a sample mean is normally distributed for any sample size. Okay, so for the second one, it's saying that if the population is normal, then any sample pulled from that population is normal, no matter if the size is 12 or the size is 42. Okay. The first one is saying that as long as you have a sample that's greater than 30, we can assume that it's going to be approximately normal. Okay, so two different kind of ideas within that. So in either case, the sampling distribution of sample means has a mean equal to the population mean. So again, we have our mean of X bars equals mean. And then the sampling distribution of sample means has a variance equal to 1 divided by n times the variance of the population and a standard deviation equal to the population standard deviation divided by the square root of n. So our variance, which is this one we haven't really seen, equals the population variance divided by n. And then from that, when we take the square root, we know that our population standard deviation divided by the square root of n equals our standard error of the mean. Okay. So the standard deviation of the sampling distribution of the sample means is our sigma X bar is also called the standard error of the mean. So remember we talked about that earlier. All right, so now this little diagram is kind of showing you the two parts of the central limit theorem. So the first one on the left shows you that you have any population distribution with a mean of mu and a standard deviation, sigma. And then you take a distribution of sample means where your sample size is greater than or equal to 30, then we can assume that that becomes approximately normal. Okay. The second one, we know that our normal population distribution, and we take any sample within that, then we're going to stay with a normal distribution. All right, so what we're going to be looking at is applications of that central limit theorem, and then finding the mean and the standard error of the mean. So this first one, suppose the training heart rates of all 20-year-old athletes are normally distributed, with a mean of 135 beats per minute and standard deviation of 18 beats per minute as shown in the following graph. Okay, so I'm going to highlight some things here. We know we're normally distributed, and we know that our mean equals 135, and our population standard deviation is 18. Okay, we have random samples of size 4, so n equals 4, are drawn from this population, and the mean of each sample is determined. Find the mean and the standard error of the mean of the sampling distribution. So our mean of our sampling distribution, remember that equals the mean of our population, so 135. And then our standard error of the mean, so our sigma of X bar, remember that equals the population standard deviation divided by the square root of n, which is going to be 18, divided by the square root of 4, which we know to be 2, and 18 divided by 2 is 9. Okay. So what it's then, by your sketch, you're just going to basically re-sketch this graph. Okay. Instead of your horizontal axis representing X or Z, like what we've seen in the past, now we're looking at X bar. Okay. In the center, we have 135. And then we're going to the left and to the right with our new standard deviation. Okay. So this is going to go to 144, 153, and then going the other direction, we get to 126, and then 117. Okay, so it's just kind of rearranging your sample means. All right, so I want you to try this next example where you're finding the mean and the standard error of the mean of the sampling distribution. Okay. All right, so now we can go an extra step and find the probability using the central limit theorem. So in 5.2, we learned how to find the probability that a random variable x will fall in a given interval of population values. In a similar manner, you can find the probability that a sample mean will fall in a given interval of the sampling distribution. We're going to have to kind of change our formula a little bit. So here, we're going to look at z equals the value minus our mean. And here we're going to be dividing by our standard error. Okay, which means we're doing x minus mu of x bar divided by our standard error, so sigma of x bar. Okay. Well, we can go an extra step and kind of simplify this formula because we know that mu of x bar just equals mu, and that our standard error is sigma divided by the square root of n. So this is going to be our new formula to find our z-scores. Okay. So during a certain week, the mean price of gasoline in California was $3.305 per gallon. A random sample of 38 gas stations is drawn from the population. What is the probability that the mean price for the sample was between 3.31 and 3.32 that week? Assume the standard deviation is 0.049. All right, so what do we know? We know our mean is 3.305. We know from the last little bit that our standard deviation is 0.049. Okay, it's not normally distributed. Doesn't say anywhere in the problem about that, but it does say n equals 38. So we can use the central limit theorem to say that it is normally approximated. Okay. So we're finding the probability that it's between 3.310 is less than x, which is less than 3.320. Okay, and this should be x bar because we're looking at sample means. And now we're going to just find our z-scores and do the same thing as what we did last week. So z equals, looking at our first one, 3.310 minus our mean divided by 0.049 divided by the square root of 38. One thing to be careful about when you're plugging this into your calculator, make sure you're using your parentheses around your numerator and your denominator, just so that way your order of operations still hold true. Okay, so this z-score is approximately 0.63, because remember we round to 2 decimal places. And then our second one, we're going to do the same thing, but we're going to change that x value to 3.32. And then if we approximate that, just going to change that 1 to a 2, and we get 1.89. So now we're finding the area between the z-scores of 0.63, which is less than z, which is less than 1.89. So we're going to find the area of both of these, and then we're going to subtract. So we pull out our tables, and we look at table 4. And the positive side, we're going to find, let's see here, the area for 1.89 gives us 0.9706 minus the area for 0.63 is 0.7357. And if we subtract those, oops, I missed a number. Sorry about that. How about positive 0.2349? Okay. All right, so I want you to try the next two examples, okay? And then we will go over them in class.